Thanks to the organizers of Atmosphere for inviting me to speak here today in the beautiful city of Krakow. This talk is about Nomad, a distributed cluster scheduler that we have been working on at HashiCorp for the past 1 year. It's open source. And this talk is about Nomad and how it helps SREs and application developers to operate compute infrastructures and applications and internet scale services on public clouds. So if you are running distributed systems, if you're running massively large number of microservices on cloud or on your private data centers or on like a private cloud like OpenStack, this talk is highly relevant. I'm a senior engineer at HashiCorp. Like you might have known about HashiCorp from one of our tools. Uh, this talk today is about Nomad. We are not going to be touching the other tools that we do. This talk is pretty much going to be on cluster schedulers and about distributed systems in general. And we are going to sort of see like how Nomad ties into the other aspects of what we do at HashiCorp, but mostly like we'll talk about cluster schedulers. So before I begin about cluster schedulers, I wanted to talk a little bit about how compute infrastructure has evolved over the last 15 years, or not even 15 years, like going back to all the way to 90s, early 90s or mid 90s. In the last decade, I think there has been a big shift in how we consume compute infrastructure. We started off with servers which were as big as probably as this room, to mainframes, and then to today's Intel-based or ARM-based servers like x86 or other CPU architectures that are out there today. And in the early 2000s, when the internet started sort of becoming popular and the SaaS companies started taking off, like that's when virtualized infrastructure took off, right? And since the last 3 years, Docker has been pretty much like the darling of Silicon Valley, and containers are all the rage. Like everyone is doing containers. What is common here is that the density of compute infrastructure has been only increasing. First, like we were running a single computer which was as big as this room, and then in the early 2000s, like we started getting like virtualized infrastructure, like VMware in the place. So instead of like running a single server or like a few server, we started packing more and more virtual servers on those physical servers. And then now we are running like containers on those VMs, right? And those containers can be on physical machines or they could be on VMs, but basically we are trying to pack as much compute services as we can on the infrastructure we have. And similarly, something has happened on the vendors as well, like from IBM mainframes, like today people go to Amazon Web Services or Microsoft Azure or Google GCP to sort of get compute infrastructure. We are seeing more and more people offloading compute infrastructure on cloud providers than like racking and shelving servers on their own. Um, so it's good. It's basically what it means is that a team is no longer bounded by how long it takes to acquire servers and to launch new services. And we pretty much like get compute services on the tap right now. Like gone were the days when we had that 15 days or 20 days cycle of like acquiring hardware and then like scaling up to our needs. Like today, like we can scale up in the evening when people are hitting our services. And when people don't hit our services, we can scale down. So that's pretty much like how things are working right now. And, uh, and the data center of 2016 is not like a data center which lives in a single place or is in a particular geographic location. The data center of 2016 looks like you are probably on Amazon Web Services or on Google Compute, and then you are peering between multiple sites of your cloud vendor, and also you might have like a physical data center somewhere, right? So you might be peering many different networks. Some of them might be cloud, some of them might be physical data centers, but it's basically like a hybrid world, right? Like some of it can be like VMs which are running on Amazon Web Services on Zen. Some of them can be running KVM, or some of your servers are just running Linux on bare metal. So this is pretty much like the scenario of 2016, like where we are today. The challenge is like it's not as rosy as like it sounds. Like it's not like we can scale up whenever we want and scale down whenever we want. Like there are some challenges with what we are doing today, right? In the new world, we have tens of thousands of servers. In the early days of data centers, human operators basically like earmarked like certain servers for certain teams. Like you would probably have like a team, centralized team of sysadmin who would basically say that, oh, there are 20 servers, and then I'm going to give this 10 server to this particular team and this 5 servers to that particular team. So it doesn't really like work that way anymore, because we are talking about not running like 5 or 10 servers. We are talking about running tens of thousands of servers. And not only that, compute clusters are pretty much like spread across the globe, and static and offline partitioning of servers no longer makes sense, right? What it means is that if you had like 5 servers, the cognitive overload of like understanding what applications is running on which servers was much lesser than what we have today. Right, when I was at Netflix, like we were running like 70,000 or 80,000 servers just in like on one Amazon region. So at that scale, like it's not no longer like viable to like earmark certain servers for certain team. Like you are going to have like a pool of compute resources, and then those compute resources are going to be consumed by whoever wants to consume them or whoever needs those resources. Cloud providers also don't play well. The abstractions and the APIs to create, for example, like storage or compute clusters, like varies very significantly across the cloud providers. Like the Amazon APIs, the EC2 APIs are vastly different from what GCP's APIs for launching a server, right? Like you have auto scaling groups in Amazon for scaling up a bunch of servers and scaling down. In Google Compute, I think it's called resource pools. So cloud providers don't have like a uniform API, and traditional ways of deployment of a service across different cloud providers and different environments like quickly gets out of hand, right? Like, I mean, we have for the last 10 years or 15 years, like we have been like struggling to deploy software, right? Like we used to first deploy software with like with scripts, right? Shell scripts or something like that. Then in the mid 2000s, like came configuration management tools, right? Chef and Puppet. They had a lot of promise, right? And we are past that era right now. We are still not like tamed, or we have not solved that problem yet, right? And as our scale is increasing, as we are doing more and more microservices, as we are doing more and more service-oriented architecture, the problem is actually getting worse. And it doesn't help that the cloud providers have so much complexity going on. So the modern cloud is all nice, but still there is a lot of underlying complexity there. And while the compute infrastructure and the cloud vendors and the vendors from whom we get infrastructure has evolved, something similar has happened with on the application side, right? Like in the early 2000s or mid 2000s, people were still doing like IBM WebSphere or something like that, right? Something which is more like a monolith, right? Like where the database and then the mid-tier and then the front end like was all packed in a single service, and then you deploy this whole bundle together, and then that would be backed by a database or something like that, and the users of your application would consume that service. And that was good, like you had lesser number of moving pieces, but then with the lesser number of moving pieces, the constraint was that now you had availability issues, you had reliability issues. Like when you had to do upgrades and things like that, it was much more involved than, say, like doing something like microservices or like service-oriented architectures where your application is backed by not a single service, but by many services. So what it means is that when you have like 100 or 300 or 400 developers working on a product, they are not working on the same code base anymore. They are working on different services. And if different services have different scaling heuristics, each of those services can be like scaled out on their own, right? Like for example, an authentication service might need stronger consistency and stronger acid-like properties for its databases, whereas a service which is doing like photos can use a cache-based database like much more efficiently. So all these different things in our product now can be different services, and that's like the trend. Like we are doing more and more of that. We are doing more service-oriented architecture now. And when you are doing service-oriented architecture and building microservices, you are actually building a distributed systems. You are actually building like complex distributed systems, and there is no getting around that. Like there is no getting around the fact that we are building distributed systems anymore. And while distributed systems are nice, that it scales well, and then it scales well, and then we can scale our teams accordingly, but they still have a lot of issues with distributed systems. The main things being like distributed systems are very complex, right? And the failure modes in distributed systems are much more complex than what we used to see in like monoliths. And at the same time, deployment strategies and rollback strategies are also complicated. Most of the times, like you don't hear twitter.com going down on Friday evening or Netflix going down on Sunday evening because system administrators are updating Twitter or Netflix. Like that doesn't happen, right? Like you will never hear Facebook going down because databases are down. So distributed systems and service-oriented architectures like come with like a lot of automated deployment, and comes with like a lot of the need for orchestrated deployments and rollback and all that. It's not only essential and important that we can deploy our software, but a lot of times software don't work well, right? I started my career at Netflix as an SRE, and what it meant was like I used to wake up as with pages in the middle of the night, and most of the times the resolution to a lot of problems is to like sometimes not to deal with a failure or like an application issue right in the middle of the night, but gracefully go back to an older version of of a well-known working version of your software so that you can get through the night, for example, right? So that your user can still consume the services that you are giving them. So it's very important that we have like a good rollback and deployment strategy for um, for our distributed systems. And all this stuff is not new, right? Like back in the day, in a data center, people used to like give names to like servers, right? People used to say that the name of a server is like Skywalker or Vader or numbers or something like that. And usually there would be an operator doing it, and then you would basically run like your applications on one of those servers. Operators would publish applications into all of these machines manually, and then sometimes you would run like one application per machine. Like you will run all your Python apps in one machine, and your Ruby apps on another, and your Node apps in another, and and then you had your database of machines with their IP address, MAC addresses, and important nodes. And if a server went offline, or if an application died, the operator was basically responsible for moving it around, moving those applications around, and fixing the machine at the same time. So what it means is that at some stage the server would get repaired, and if a server failed, it would get repaired, and then someone would basically update the spreadsheet where the server where the new application resides, and it's basically like a set of registry, and the registry would contain the IP address of your application and the server on which it is running, and when it was last deployed and things like that. And to make it highly available, we had a solution. We would give those sysadmins a pager, and whenever something would break, like we would page our sysadmins, and they would come and fix our servers, and they would update the spreadsheet, and it would be all good. But this obviously doesn't scale. So what is the solution? What is the solution to that? What is our solution to running tens of thousands of servers on the cloud where things are healing, things can heal without manual intervention, where we can deploy software as much as we want, where we can roll back software as much as we want? We need something called a cluster scheduler. And cluster scheduler are essentially provides us like these three things, right? What cluster schedulers provide us is that they allow us to treat compute infrastructures as like a pool of infrastructure, right? Like as a pool of CPUs, right? We no longer need to know like what is the name of a server, what is the IP address of a server, or which availability zone, for example, in Amazon does a server reside. What a cluster scheduler provides us is that like these are the resources that are available, and as developers or as application developers, like all we need to say is that we need to run our application, and those application needs to be running on certain number of CPUs or certain amount of disk and all that. And cluster schedulers should provide like better quality of service. So in the early days, it was the sysadmin or like the operator who would provide the quality of service. And now, since we are running so many servers and so many number of our applications, it is no longer possible, as I was saying, that it's no longer possible to scale the manual mode of like adding people or having people fix our servers or fix our applications. It's the job of the cluster scheduler now to provide that quality of service. And also at the same time, since we are running so many services on so many machines, it's the job of the cluster scheduler to provide higher resource utilization. Back in the days, again, like system administrators would find out that, oh, this machine is at 60% utilization. We can maybe get some more utilization out of this machine by running few other extra applications. So all those things are services that a cluster scheduler provides. And that essentially is Nomad. So Nomad is a cluster scheduler which provides all those things that I was saying, and it is multi-data center, it is multi-region, it can run flexible workloads, it does bin packing, and it scales to like tens of thousands of machines, can run up to a million number of services, and it's operationally simple. I will go into like each of these things in detail in later slides. But what I wanted to impress upon you is that the challenges that I said so far is that today in 2016 we are running on multiple different data centers on multiple different geographies. If you're running on Amazon, you're probably be running on US East 1, you're running on US West 2, you're probably running in Dublin and now in EU Central 1 because you probably have a global user base and people access your services from different parts of the world. And if a data center fails, for example, if Virginia fails, or if Frankfurt fails, in the data center in Frankfurt fails, you would like to be running your applications out of Dublin or Seattle or some place like that, right? So that like you can actively move traffic from one data center to another. So that kind of support, multi-data center and multi-region support is something that we have built from the ground up in Nomad. Um, I will come again, I'll come into like flexible workloads and what it means. But so far, like what I wanted to impress upon is that the scale that we are talking of running service-oriented architecture, like the scale at which like we are going to be running our applications for the future, are only be going to be facilitated by cluster schedulers which are not bound to a single data center. Because a data center, a rack, or a physical place can fail, but unless like we have we run our applications in an active manner across many different geographical locations, like the modern internet scale applications are never going to get to the place where like where you would like them to go. So, what are the things that a cluster scheduler provides? The things that the cluster scheduler provides, as I was saying, is higher resource utilization. That means a scheduler has to bin pack. So what it means is that if your servers are like bins, right, like where every server has certain amount of capacity, the cluster scheduler should be automatically be packing as many services as it can on a single machine. So you as an operator, you should be able to say that I want all my machines to be at 80% load, right? And I want all my certain machines, for example, which has certain CPUs or certain type of disks, you want probably like say 95% utilization, or certain machines which has lower amount of network, like you would want maybe like a lower amount of utilization. So the scheduler should be bin packing as much work as it can accommodate as the operator wants it to. So the earlier mix and matching of like applications that the operators used to do, like Node.js, some Node.js applications and some databases running on a single machine, the scheduler should be doing all that on your behalf. And then at the same time, like schedulers should also be doing job queuing. So what it means is that if you have 5 teams in your company, and one of them is running like batch applications and the other is running front-end services, so what it means is that probably the front-end services are more critical, right? Because those are the services that the end user is accessing to get your website or your mobile application or something like that. Whereas batch applications might be something that your machine learning teams are running to get to crunch data and stuff like that. So if a scheduler doesn't do job queuing, what might happen is your batch applications might consume the whole cluster, and you might be having like no more resources to run your front-end application. So a scheduler which has to cater to the whole organization should have the capability of queuing jobs and having priorities of jobs, so that like a team cannot take down the whole compute infrastructure. Decoupling work from resources, what it means is that, as I was saying, today, like in 2016, like we have all these different cloud providers having different APIs for launching compute infrastructure. What we want is our developers to be hidden from that complexity. Like developers should not worry whether they're running applications on Google or on Azure or on AWS. Developers should be given like a common API, like an API which they can express the work that they are running, right? If you are a Node.js developer or a PHP developer, like why do you care about like what is the API for Azure, right? You should be able to express that this is my application, this is the entry point of my application, and my application needs 5 CPU cores and 160 GB of disk or 20 GB of disk, and I want to run 5 copies of this. And I want to run 5 copies of this in Seattle, 10 copies of this in Dublin, and 5 copies of this in Frankfurt maybe, right? And that's what you want. Like you don't care about what is under the hood, what is running under the hood. The operators, on the other hand, like the site reliability engineers, they care about like what is the compute platform and things like that. So there is a difference between the different people in the organization. So a cluster scheduler should basically be decoupling all that from the developers. And the scheduler should also isolate resources. So if you're running a database and a PHP application on the same machine, if for example, there is some bug in the PHP application and there is a tight for loop, the PHP application should not consume all the resources, all the CPU resources. Like it should only consume the amount of resources that it is allowed to have, and then the database should be given the resources that it wants. So it's the job of a cluster scheduler to basically like containerize everything and make sure that the quality of service is given to each of these applications that they want. So what we need is we need a job specification. And the job specification should declare like what to run. And so in Nomad, we have a job specification like this. So if you're a database operator, you can define something like this, job Redis, and then you can say that I want to run my Redis in US East 1, in the data center US East 1. You can add like multiple more databases, more data centers, and then Nomad will run the services in each of these data centers. And then you are going to say that I want to be running a task in this job, which is called the Redis, and then I want to use Docker, for example, to run my Redis database. And I want 500 megahertz of CPU, I want 256 MB of RAM, and you can say that there is also a key here called count, which I have not shown. You can say that count equal to 10. I want to run 10 Redis in each of these data centers. So now as a database operator, you no longer are worried about whether it's Google or whether it's Azure or anything. Like you are basically telling the cluster scheduler that, hey, whatever compute resources you have, I want this many number of Redises running in each of this data center. And then Nomad will determine where to run and how to run, right? You are saying to use, you as an app, like a database operator might be saying that I want to use Docker to run, and then Nomad, it's up to Nomad to configure Docker the right way, to configure the volumes the right way and everything to run Redis actually. And what is critical here is that it allows Nomad to abstract work from the underlying resources, which is the primary function of the scheduler. And Nomad supports multiple clouds and DCs and region. So the main construct for different geographies in Nomad are twofold. One is data center and the other is regions. So you can have multiple data center in a single region. So if you are, for example, if you have like US, if you're on Amazon, you can say that US East 1A is a data center, US East 1B is a data center, and US East 1C is a data center, and US East is like the top level region. So then if, for example, one of the zones in Amazon dies, then Nomad is going to rebalance the work across all the other zones in Amazon. If you're in a physical data center, you probably have a site, and in a site, you might have multiple buildings. So in that case, like a site will be a region, and then the different buildings of your site are going to be like the different data centers. And each of these data centers might have like different power supplies and things like that. So the job spec is basically like the common unified interface that Nomad has across all the different cloud providers. Like you can run a single Nomad cluster that can span Amazon, Google, and Azure. Like there is no problem. Like you will be basically be running Nomad clusters in each of them, and Nomad will talk to the other Nomad clusters that it is configured. And as a developer, like you are no longer then like targeting a specific cloud. You are basically saying that Nomad, I want to be running this in this location, and then wherever there is capacity, Nomad will pick like a spot. So within a region, like this is how everything looks. So the main components of Nomad are a Nomad client and a Nomad servers. So Nomad servers are basically like the schedulers which do the scheduling, and Nomad client is basically the servers on which your application runs. So a Nomad server is, you usually have like 3 or 5 Nomad servers in every data center, and you usually have like up to like say 20,000 or 30,000 Nomad clients. And the reason why you would have 3 or 5 Nomad servers is that even if like a server fails or a rack fails or a switch fails, you want like multiple copies of the server running so that you get higher availability. So what we do is in the Nomad servers, we replicate the data that each of the servers have. So whenever like the scheduling happens, like the data is replicated across all the Nomad different Nomad servers. But as a user, you don't need to know which Nomad servers are running or which one is the leader. Like you can talk to any of the Nomad servers that, hey Nomad, I want to run this application in my data center. And then Nomad server is going to forward the request to the appropriate the Nomad leader server, which then does the scheduling and dispatches the work and everything. And then once the scheduling happens, then the clients pull the information, and then they are basically running your application. And this is how multiple regions work. So if you, for example, if you are running Nomad across 2 different regions on Amazon, or even running Nomad across 2 different cloud providers, you will basically have 2 different Nomad clusters, and you will basically connect each of those Nomad clusters over the internet. So what it means is that if you have a data center which will have very low latency connections, and if you have another data center which is a different part of the continent or different part of the world, they don't need to have like a fiber optic connection between them or something which is really high-speed internet connection. If it's a common internet connection like between those regions, like it's fine. Like we basically do replication of the jobs over the internet. And if you want to submit a job for a different data center or a different region, and if you hit your local data center, Nomad will forward the job request to the appropriate data center. So as a user of Nomad, you no longer need to like hit even the right servers, Nomad servers. Nomad knows what are the other Nomad servers that are there. And a region is an isolation domain. So what it means is that we don't recommend a single Nomad server or a cluster of Nomad servers to control clients in different region. The reason why we do this is because we have seen that on the public cloud, mostly faults happen at the region level. Like you would hear Amazon having outages in US East 1 or US West 2, but very rarely you will see that they are having outages in multiple different Amazon regions. Recently, there was an outage in Google which affected all the Google regions, all their data centers and all their regions, but that was because they messed up some BGP configuration. So not much can be done when you mess up your network configuration. But other than that, like in the last 5 or 6 years, I haven't seen personally cloud providers having faults at more than one region at the same time. And also the network connectivity between servers in a single region is of the order of 10 to 15 millisecond, whereas like network latencies between, for example, US East 1 and US West 2 is like, I think it used to be 70 milliseconds or 85 milliseconds. So which is like not so nice for cluster schedulers which have to take decisions in a very quick manner. So it's really essential that you run Nomad, Nomad within a single region and connect them over the data center, but you can have more than one data center in a region. And a region is usually the scheduling boundary. And the data model of Nomad is really simple. We basically have evaluations, and every evaluation results into an allocation. So whenever like you submit a job, we create an evaluation under the hood, and those evaluation results into like an actual running allocation. An allocation is basically like a representation of your job running on a node, and nodes basically don't know anything about the job that you have given, but node only knows about the allocations that the schedulers are creating. And evaluations are state changes, and this is something which is very different than other schedulers that are out there like Kubernetes or Mesos. Those schedulers are not event driven. They're basically like sort of like they run the scheduling algorithm every 100 millisecond, and during every scheduling cycle, they're basically taking decisions of what to run and where to run. Whereas Nomad is completely event driven. Whenever like something happens in the scheduler, or in the cluster, like we create an event and the schedulers respond to that. So, for example, like if you delete a job or a node goes up or a node goes down, that is an evaluation, and the schedulers run against that event. So if a Node.js app dies somewhere, that will be an evaluation, and the scheduler will react to that event and put that Node.js app on some other machine or restart that Node.js app. So think about evaluations as a function and that the scheduler basically has, and then it creates allocation updates. And then the scheduler basically, we have multiple types of scheduler. We have service schedulers, we have batch schedulers, we have system schedulers. So each of these act on the evaluations and they create allocation updates. And the scheduler is completely concurrent. There is no head of line blocking. So some team might submit like 10,000 jobs, and some other team might run 5 jobs, but because someone is overloading the scheduler, like it's not like that other team which is running smaller number of jobs is not going to get scheduler time. And this is again very different from how most schedulers on Mesos works today, or most schedulers on Kubernetes work today. So we have no head of line blocking. The client architecture is simple. Like we have broad operating system support. We run on, Nomad runs on Debian, Nomad runs on RHEL, any Linux distro. Nomad runs on Darwin. Nomad, I think someone actually ran Nomad on Raspberry Pis the other day. And Nomad has pluggable drivers. What it means is that, I'll come to the drivers a little later, but it basically means that you can run different types of workload. Most schedulers these days run Docker, but with Nomad you can run like a VM, you can run your C# binaries, you can run Java binaries without even using Docker. And drivers are something which execute tasks and and then they do the resource isolation. So I was saying that schedulers should do the resource isolation. That actually is the task of the drivers that we have. And today we have like this many drivers. We have Docker Rocket, which does containerization. For running VMs, we have KVM and KMU. And if you're running Java or static binaries, then you can run without any of those containerization. And we will just run those binaries on any machine which has capacity. Besides that, there are other drivers in the pipeline. Nomad is going to come up soon with the support for Windows Server containers. And we are going to support Zen and Hyper-V as well. Hyper-V is a virtualization technique that Microsoft has. And very soon, there will be a C# driver as well. So you should be able to run C# without any other dependency. And as an SRE, I think these are like some of the features that I really like. Nomad has maintenance primitives. So what it means is that when a node is going bad, in the middle of the night, you don't need to do anything. You basically say that Nomad node drain, and give the ID of the node, and Nomad will move all the applications that are running on that node to another node. So this is useful like when you have like a hard disk failure, or someone is saying that, oh, this something is happening, something funky is going with the networking on this node. So you basically don't need to do any troubleshooting. Just do Nomad drain and that machine is gone, and then you can terminate that machine if you're running on the public cloud. If you're running distributed systems, Nomad provides a very dynamic network topology. There are applications which are always coming up, applications going down, nodes going up, and nodes going down. So you are always using things like console or like Zookeeper or something like that. So Nomad is service discovery aware. So if you're running jobs on Nomad, Nomad will automatically register your tasks or your services with console. Like you don't need to do any other configuration. You define that this is my job, and these are the services that gets exposed, and all the service registration, removing the services when the task goes down or the task moves from one node to another, is all done by Nomad. This is how the service discovery looks. You define a block like service, you name the service, and if you have any health check and things like that, you define them, and Nomad will keep it synced with console. System jobs. So as operators, we run like monitoring systems and log shipment tools, and then metrics agents on every machines in the cluster. So we have something called the system job scheduler. What it means is that there are a certain number of jobs that you can run on every machine. Like you can run your monitoring system thing on every node of the cluster. What it enables you is that if, for example, you want to update your monitoring system agent, you can use the cluster scheduler now to update. So when last year there was some issues with the SSL, OpenSSL, like in a lot of companies there were like, people were rushing to patch servers and things like that. They were making new AMIs, they were deploying servers and things like that. But if you have with something like system jobs, like you can put your metrics agent or your, or your tools in like a Docker container, and then you can say that that's a system job now, and you only change the Docker container, and then it goes, system jobs would basically like go into every node and change those tasks, those system level tasks, and now you don't need to change anything at the OS level. So I think I really like system jobs, and they are one of my favorite features. Nomad also does log management. Nobody usually pays any attention to logging unless like things go wrong. And Nomad does log rotation for applications. What it means is that you as an application developer can say that I want 50 MB of log retention on this machine, and anything beyond that, Nomad is going to rotate it automatically. And we are also doing log forwarding right now. So applications don't need to do anything else. As long as they are writing to standard out and standard R, Nomad will forward those logs into like Logly or like or a remote syslog provider or Splunk and things like that. We get questions of like how is Nomad production ready, and we wanted to know whether Nomad is production ready too. So a few months back we did this benchmark, and we ran like 1 million containers on Nomad, and it took us 5 minutes to schedule 1 million containers on Google Container on Google Compute Platform. And there were like host failures and there were node failures and things like that, and we could see that Nomad could consistently run 1 million containers, and when there were failures, it would move things around. It's an open source project. It's on GitHub, and the website is nomadproject.io, so take it for a spin. And file issues if there are anything, and let us know what do you think about the project. So that's all I have. Do we have any time for any demos or anything, or is it, do we have time? Cool. So let me do a quick demo. I was rushing towards the end. I was not sure if I had time. So let's run like the Redis thing that I was showing. Let's see how it works. So this is the job specification. Can you see this thing, or no? Okay, is it visible now to everyone? So this is like a job specification. And in the job specification, you give a name to the job. So it's an example, but like we can change it to something else, right? We can say database. or something, right? And then we are saying that data center is like DC1. DC1 is like the default data center. You can add things like DC2 and DC3 and whatnot. But DC1 is the default data center. And then the type of the job, like you can define what is the type. By default, it is service, but you can say like it's either a batch. You can say it's a batch, or if it's a batch job, or if it's a system job, like a log shipping agent or like a metrics or a monitoring system, then you basically say it's a system job. But this one is a service. Like a database is a service. We don't want the database to ever go down. If it goes down, we want the cluster scheduler to bring it up again. Whereas batch, like if a batch app goes down, like we would restart it maybe like 5 times or 10 times based on what you want, but it won't like be running indefinitely. Service jobs, on the other hand, will run indefinitely. If there is a node failure, Nomad will push it to another node. If there is a transient failure, it will restart it after a few seconds on that node and things like that. And then you can say, what is the priority of the job, right? The priority of the job is something that you determine as an organization. Like my job can be more of lower priority than your job if I am running something less business critical. So a priority is basically nothing but like a numerical, like an integer. You can compare priorities with niceness of an operating system. So if you're running Linux, like every process has a niceness. So that is what like the Linux operating system scheduler uses to know like how important is a process. So you can define like what the priority of the job is. And then you can define constraint. You can say that I want this job to be running only on kernels which are Linux. Or you could say that I want this job to be running only on Macs. So in that case, like you will say that the kernel name is Darwin. In our case, we want to use Linux, so we will just like revert it to Linux. And we want to define what the update strategy is. Like you can say that I want, if I'm running like 5 services, I want to stagger when I'm updating, like a rolling update or something. I want Nomad to update at like 10-second interval each of these. And I want Nomad to update only one service at a time. I'll come to that later. And then there is the concept of a task group. So what it means is that a job can have multiple task groups, and the task groups can have like multiple tasks. So imagine you are running like a database, and you want to also ship the logs of the database, or you want to have like a application which is doing backups every 15 seconds or something. So then what you could do is you can have like a group, and you can have like 2 tasks. One is a database task, and the other we have not shown, but this can be like a like another task which does backup. And then you could run your backup task here, and then the database task and the backup task are always going to be running together, because the backup task will be running on the same machine where the database is going to run, right? And if any of those tasks fails, both of those tasks will be restarted. So now let's go to task, right? So in the task, like we define this is a Redis task, and we want to use the Docker driver. And then the configuration of the Docker is we want to use the Redis Docker image, and then we want Nomad to be forwarding some ports, right? We know that Redis is running on 6379, so we want Nomad to be running, doing some port forwarding here. And whenever the task starts up, we want Nomad to register this task with console as well. So we basically say that this is the tag, and this is the name of the service and all that. And then we say that the resources of the task are CPU is 500 megahertz, and memory is 256, and network we need a 10 megabit link, and assign a dynamic port to me, right? It can run on any port, and it doesn't matter. And since we are using console, we can always discover the port of the service from console anyways. So this is like a task definition. And then we can also say that do log rotation and only have 15 log files, and each of those log files will have maximum file size of 10. And once you have defined this, all you need to do is go here and run Nomad. So Nomad is a single binary. It doesn't have the additional complexity of running multiple processes. Run Nomad. So I'm running Nomad in the dev mode. I'm not creating a cluster right now, right? And then all I need to do is I need to do Nomad run example, and that's it. And we will see that Nomad is going to be starting, starting the Docker container. So if you see Docker PS, you'll see that Nomad has just started it, and we said that give me a port, give me a dynamic port. So Nomad has given this port 49187, and it has forwarded it to 6379, which is here, the port map. So yeah. So and it has basically giving it an ID and everything. I'm not running console right now, so you won't be able to see the console registration bit. But this is basically like how things work. And now, if you want to update Redis, I don't actually know what other Redis containers are there on Docker Hub. Let's see what else Redis has. But basically, for example, if you want to update from Nomad Redis latest to a particular version like Redis 3.0, because the latest edition of Redis has some issues, all you need to do is change the image, and then since you already have this update strategy defined, Nomad is going to update each of those containers, and it won't update everything at once. It will update one at a time, and then it will put a delay of like 10 seconds between each of these updates. Because if all the Redis instances dies, like might have an outage. So that's basically how things work.